Good morning. So today we're going to talk through section 15.2 in your text. The topic is pressure. We've already talked through density. Now we're going to talk through pressure. And the reason we're going to discuss pressure is because before we get to the next section, fluid pressure, we need to understand the concept of pressure. So we're in section 15.2, page 304 and 305 in the text. So let's get started. So as with a lot of our equations we've talked about so far, it's a rather simple one, and you can see that on page 304. So the equation is pressure is force divided by area, and you see it abbreviated like that. Capital P for pressure, capital F for force, capital A for area. So a few days ago we did a quick geometry review. So this is one example where you'll have to be able to calculate area if necessary to be able to calculate pressure. Now let's talk about the units. So first off, in the metric system, what might be units for pressure? So you have force divided by area, and I believe we may have already talked about what units of force are in metric. Actually, we talked about weight. Remember, when we were back, we spent a very brief moment a few days ago talking about the conversion between weight and mass. So this was back in chapter 7, and we talked about using this equation to convert between weight and mass. For instance, if you're given mass, you need to calculate weight. You multiply by acceleration due to gravity. Now, weight is a type of force. So weight and force will have the same units. So if you remember when we were doing the conversion between weight and mass, weight in metric had the units of newtons. So it'll be the same, force is the same as weight in that respect. And then what might be some units for area in the metric system? So the metric system always will default to standard units. So the standard unit of length in the metric system would be meters. So area in this case would be square meters. So typically you would see the units abbreviated this way, newtons per square meter. Now we have another situation here where we have a unit named after a person. So if you'll take a look on page 304, it tells you that 1 Newton per square meter is equal to 1 Pascal. So 1 Newton per square meter is equal to 1 Pascal, which is commonly abbreviated as uppercase P, lowercase a. All right, now we'll go to the English system. So what might be units of force divided by area in the English system? And as I said before, force and weight take on the same units. So weight in English would be pounds, and area could be either square inches or square feet. a lot of times you'll see square inches is more common. And you may also have heard of the abbreviation PSI. So PSI is just an abbreviation for pounds per square inch. PSI, pounds per square inch. So you'll see that kind of a marking, for instance, on your bicycle tires for air pressure in your tires. You also see PSI related to car tires for air pressure as well. So that just means pounds per square inch. Now there is a conversion, if you had to, there is a conversion in your textbook. If you look on the conversion table on the inside cover of the text, there is a section for pressure, and you'll see conversions between newtons per square meter and pounds per square inch. And as with all conversions, there's two different versions of this conversion. And a newton per square meter and a pounds per square inch are wildly different. You'll see in this conversion that you have almost 7,000 newtons per square meter, not quite per pound per square inch. So they're very different units. Okay, so now let's do an example problem. Let's work the example that's shown at the bottom of page 304 onto 305. Now this example, 15.2, is done for you in the text in metric, but to understand it a little better, let's work it in English. Alright, so I don't know if any of you are golfers, have played golf, or familiar with golf, but in golf, just like in some other sports, it is common for golfers to wear golf shoes. And golf shoes have cleats on the bottom, much like, say, soccer shoes or other kinds of sports shoes that might have some kind of a cleat feature on the bottom. Now, this example is, what this example is having you figure out is when a golfer is wearing golf shoes with cleats and then at the end of a round walks into the clubhouse to have a beer or whatever, how much pressure is that golfer exerting on the floor inside the clubhouse? Now years ago, you typically won't find them anymore except maybe among professionals, but for amateur golfers, the golf cleats now are like kind of a soft rubbery material. But years ago they used to be made out of steel, and they were small and pointy and very different from what you see now. So this example, this first version of this example I'm going to do is with the old style cleats, which were like steel studs, and so they could dig into the ground out on the course effectively. So here's an assumption we're going to make. So again, we're going to do this in English, and we're going to make a lot of assumptions just to make this easier to calculate. So let's say the golfer has a weight of 180 pounds. And we're going to also approximate the size of the golfer's shoe. So we're looking at the area on the bottom of the shoe, and we're just going to make an assumption. It'll be close enough. So let's say the golfer's not wearing a rectangular shoe, but it makes it easier to calculate. So 10 inches by 3 inches is a pretty good approximation for the dimensions on the bottom of a shoe. So then you can calculate the area on the bottom of the shoe, which would be 10 inches by 3 inches or 30 square inches. However, with the cleats on the bottom of the shoe, and we're going to put 10 cleats on the bottom of the shoe. So what we're making the assumption is that when a golfer is walking on a floor inside a building like the clubhouse, it's the cleats that are exerting the pressure on the floor, not the whole bottom of the shoe. So we have to make an assumption about each cleat. I'm going to blow this up out of proportion. Let's say, to make it easy, the bottom of each, the end of each cleat is square, and it's about 1/10 of an inch by 1/10 of an inch, which is probably pretty accurate for those kind of cleats. So now you have to calculate the area at the bottom of all 10 cleats. So each cleat would be 1/10 of an inch times 1/10 of an inch, length times width, and then you also have 10 cleats. So the total area of the cleats then would be 1/10 of a square inch. So the other assumption we're going to make is we're going to make the assumption that as the golfer is walking on the floor, there are moments when you put one foot down and you lift the other foot up, there is a moment in which all of your weight is going down through one foot. So there's a moment when all of the 180 pounds is being transmitted through this area, which is only 1/10 of a square inch. So now we can apply our pressure equation. Pressure is force divided by area. In this case, the force is the weight of the golfer. And there is a moment when it's those 10 cleats that are transmitting the force down to the floor, and that's 1/10 of a square inch. And if you divide 180 by 1/10 of a square inch, what do you get? In this case, it's a very, very big number. It's 1,800 pounds per square inch. Does that sound like a big number? It is. It's a very big number. And because of that, those kinds of cleats are typically not allowed by golf courses anymore, because that pressure being exerted on the floors in the clubhouse was so great it was poking holes in the floor and causing damage to the floor. So that's why the transition in recent years to the more plastic type of rubbery type of cleats on the bottom of the shoe, so they do not cause damage, because those are made bigger around, maybe as much as a 1/2 inch around, with little sharp edges on them. But again, it's rubber, so it's not going to dig into a floor. Okay, now to contrast that, what if somebody walked into the golf clubhouse and they weren't wearing golf shoes? They were just wearing regular shoes with no cleats on them. So this person's 180-pound weight was being transmitted through the whole bottom of the shoe. And again, we'll assume that as this person's walking, there's moments when all of the weight's being transmitted through one shoe. So now, we already calculated the area of the bottom of the shoe is 30 square inches. So we can redo this calculation for this situation where the area is 30 square inches. And what is 180 divided by 30? So that ends up being 6 pounds per square inch. So you can see there's a vast difference here. In the first case, all the weight was being transmitted through a very small area and with sharp points, small points. In this case, it was just a flat shoe. So there's an example for you of calculating pressure. And we pretty much followed example 15.2, but we just converted it over into English. All right, now there was a worksheet you were working on the other day, and for density, this was worksheet number 1 on pages 61 through 63 in the workbook, and there was one problem you couldn't do because we hadn't covered pressure yet. So let me give you the necessary information for that one, and then you can do your calculations. So now we're in the workbook, page 62, problem 4. Okay, so the idea here is that we have this brick that's illustrated for you in the worksheet, and we're going to calculate the pressure that this brick would exert on a table. In one case it's sitting this way, in the other case it's sitting up this way. So the brick in either case has the same weight, but the area through which the weight is being transferred is different. In one case it's this area, in the other case it's that area. So let's go ahead and take the dimensions, measure the dimensions of that brick. So let's measure the dimensions of this brick. So I'm just going to use a ruler. Measure, we're going to do this in English. So we have one dimension is 7 3/4 of an inch. That's the long dimension. And then we have the short dimension is, it looks like it's 2 1/4. That would be this one. And then this dimension right here then is going to be, looks like 3 1/2 inches. Okay, so those are your dimensions. So for the bottom surface, you'd use these two dimensions to calculate area, and for this end area, then you could use these two dimensions. The other thing you need is the weight of the object. So we'll have a scale, and we'll just measure the scale, and that weighs out at 3 pounds 3 pounds and 11 ounces. So you'll have to do a conversion, convert this to pounds. You'll have to convert the 11 ounces to pounds and add it to the 3 pounds. So you'll be working in decimals. So you can look up the conversion between ounces and pounds. So you can work that problem on page 4 and or that problem 4 again on page 62, and then you can ask questions about that tomorrow. And then the next topic we're going to move on to then will be fluid pressure, starting on page 305. All right, that is all for today.